back. Now I am going to start describing how to connect the excess function and partial miscibility to understand the stability of the phase. Okay. So, the reason we are trying to understand this is because our interest is to understand whether the system is stable or not. Now, for stability, if you recall, we always talked about the second derivative of the free energies, okay, to be greater than 0. Okay. So, in other words, if you have a mixture, then your interest is basically to look at second derivative function, and this must be 0 for a stable phase. Okay. So, let us consider a system here where you have a mixture of two liquids, let us say 1 and 2. Okay. Now, you can write down this total GF mix as simply the component or contribution from the pure phase plus the change upon mixing. Okay. Now, let me just draw this particular function, if you look at here with respect to n, this is equivalently, you can also look at, instead of just del of g, you can also look at del of delta g. Okay. So, del of delta g also is equivalent statement if you are looking at it here. So, let me just draw an interesting curve here. So, what we are interested is something like this. So, this is basically I am plotting del mix g here, okay, as a function of composition, okay, and beneath here we have temperature versus composition, right. So, typically when you look at, if you recall your simple vapor liquid concept phase diagram, then usually this is kind of a curve where this is your binodal curve, okay, and we always talk about what would be the typical free energy at this point, the second derivative. So, since it is this, so you would expect the del of any mixture delta G with respect to composition will be also greater than 0 at this case, because these are the stable phase. Okay. So, correspondingly at T1 you may have something like this here, okay, pretty much stable phase where is concave up. Okay. Now, if you increase the temperature, you may see something like this, something like this. Okay. Now, this part here, if you look at it, this part, the second derivative x2 at this pressure and temperature will be 0, here also it will be 0, right. Okay. Now, this corresponds to somewhere here, okay, where I am going to draw this corresponds to some point here at this temperature, okay, these 2 points. So, this is called spinodal, okay, where this is the line which corresponds to the second derivative of the, okay, the gives free energy 0. This range here is our outside is a stable phase, and this is actually the metastable part, where the second derivative here at the temperature is pressure is greater than 0, okay, in both the case. Here this is also true, this is also true. Now, looking at here again, if you look at it here, this is your point A, So basically this is, so what is happening, this is concave up which is stable, concave down. So if you have a system concave up, it will try to segregate in such a way that it will end up somewhere here. The phase separate segregate such that the composition is closer to this part. So this is your composition, initial composition. It may segregate in such a way that it becomes x1 star, x2 star. Okay. So and this of course can be connected by a tangent correspondingly. So this is something which one can prove it also. So the instability criteria is second derivative of g mix x square pt less than 0. This also implies that second derivative of delta m part here g by del x square pt is less than 0. Okay. So this is something which comes directly from this analysis. Now let us try to introduce an excess function so let us define GE with respect to the excess, means with respect to ideal solution. Okay. So it's going to be G mix, okay, minus RT x1 ln x1 plus x2 ln x2 minus x1 G pure minus x2 G pure 2. Okay. So this is the G of x. All right. I am going to take second derivative of this plus, so if it is unstable, then this will happen, this condition will meet, isn't it? So if you use this, you can show that this condition is equivalent this. So this is for instability. Now why I have to do that? Why I have to change this thing to GE, and again I take the second derivative, since this is going to be less than 0, I rearrange, so this is what I get. So this is why I have to come up with this expression, because GE can be connected to activity and other models, and that is the reason. But this depends primarily on the way it is. So if you change this system to some other thing, you may not see this kind of curve, you may see this kind of curve also. So it primarily depends on the molecular nature of the system individual components. We have introduced the excess function in this way with respect to the ideal solution, okay, and then we got this expression, because of course the second derivative of this with respect to x is going to be less than 0 for instability. So we can write in this form, and now I have an expression in terms of Gx. Okay. So for ideal solution, what is the Gx? Going to be 0, right? Because that is with respect to ideal solution, right? So Gx is 0. This will be for all x value, which essentially say the inequality. So if this is 0, that means inequality is never obeyed for ideal solution. You will not see these things, okay, because all these are positives. Okay. So that means the ideal solution is always stable and cannot exhibit any phase separation or splitting, right? Always stable. Okay. Now let us try to understand a bit more by considering a model. Okay. So let us consider the one constant Margulis model, where the model is A is equal to AX1, AX2, right. So the question is, what would be the variable A for which the stable phase exists, or in other words, what would be the variable A for which the phase or the system will be unstable. So we can plug in here, we can take the second derivative, right, Tp, this is going to be So I can write this in terms of x1, a x1, 1 minus x1. So this is going to be minus of 2a. Okay. Now 2 minus of 2a plus RT, this term should be less than 0. Okay, then this will give us a condition of A. So I can write this or minus 2a plus RT 1 by x1 plus by x2, okay, less than 0, or 2a greater than RT by x1 x2. So if you plot this RT by x1 x2 as a function of x, it will look like this, where this is nothing but minimum value is going to be 4 RT. Okay. So what is the smallest value which satisfies the above inequality? Value of A which satisfies the above inequality is going to be 2 RT, right, and the corresponding composition would be, right, this is the critical composition, right. So you are saying that A should be, maybe satisfy the inequality, should be this is small greater than 2 RT, right. Okay, so this is a very simple exercise which you have done. Of course, you can actually use some other models also and come up with the parameters which for which stable or unstable phase occurs. Okay. So essentially, what it tells, this A characterize the stable and unstable phase. So there is a border line between this stability and instability, and this border line is called sometimes incipient instability. Okay, so it's like more or less it also gives you the idea of the critical state at which this things will not be stable or something like that. So it is basically also suggests that it corresponds to a critical state. Okay, this is the borderline, right? It also one can find out by looking at the second and third order. So basically it occurs when 2 points of inflection merge into single point. Okay, well, this may look very complicated statement here, but in a simpler way this is characterized by looking at simply the second order should be 0 or third order to be 0. Okay, that is what it looks like this. Now in this case the consolate temperature is another statement which another variables which we would like to emphasize. Now for example Tc, which is we call it consolate temperature. Okay, for the one parameter Margulies equation is given by A by 2R. So recall that this was the minimum value of A. So the T which corresponds to such a thing would be the critical temperature, which we call in this kind of system as consolate temperature. Okay. So now I will try to use this one parameter Margulies equation to describe different kind of phase diagram which we obtain, okay, for different conditions. Okay. So, I am going to describe different ways the A could be, okay, for different system. So, let me first draw temperature versus composition, okay. And what we have here is something like this, okay. So, in this case this is a two phase, this is a one phase, this is nothing but Tc, and this is called upper critical solution temperature, UCST, okay. This is again two phase, this is one phase, all right. So, here this is your UCST and this is your LCST, okay. Here is two phase, this is one phase, this is called LCST, okay. This is two phase, this is two phase, this is one phase, and this is a little bit interesting because this is called LCST and this is called UCST. The curvature top, the way it is there, concave down, will be UCST. The corresponding A values which allows this kind of phase diagram, let me draw that now. So, it is going to be T, and we are talking about A by RT, okay. And A by RT is 2 when you are talking about the conditions or the minimum value for the instability, okay. So, let me draw here, this is the 2 value, okay. So, this is your value. So, this is the temperature which is now corresponding to UCST. This is 2 and this is 1, okay. This is the one we have, the other one is going to be like this and this is another one, okay. So, this one would be your LCST, this one is your UCST. Again this is two phase up, this is one phase, okay. This is two phase, this is one phase. So, this is corresponding to LCST, this is UCST, and this is UCST and this is your LCST. So, it is not always that LCST has to be lower than the UCST, because I think this the way it is done is basically the way the curvatures. But anyway, the point was basically that this A, the nature of the A with respect to temperature governs the way the phase diagrams are, okay. And this is something for a very simple system tells you this such a complicated phase diagram, all right. So, I hope that you got an idea of the way we calculate the instability, okay, and how we can relate G axis, okay. Different models can be used to identify the conditions for which this phase diagram or phase separation occurs, okay. So, with this I will stop, and the next lecture I am going to start theory of solutions, okay. So, see you in the next lecture.